Great. Okay, thank you. As George pointed out yesterday, the first decade of IOA was marked by very active research on relativistic astrophysics. And two threads of that research that were particularly important were jets and supermassive black holes. On the jet front, there was a breakthrough by Martin Rees in 1966 who pointed out that if you have a source that's coming towards you at relativistic speed and radiating, the speed at which it approaches, the speed at which it can change its vary, it can be speeded up tremendously by the very simple light travel time effect. So as the emitting region comes towards you, it takes less and less time for any emitted signal to reach you, and basically any changes that are emitted get compressed from your point of view. If the source is not precisely coming towards you, this is the effect that gives you the apparent superluminal motion. As VLBI observations started to reveal actual jet-like structures on the sky, it became clear that, these jets did exist and they were moving at highly relativistic speeds. And one outgrowth of that realization is the model we have today for blazars, which are AGN with jets relativistic jets pointing nearly towards you. And that model was proposed in 1978 by Roger Blanford and Martin Rees. And if you go back to the original conference proceeding at the Pittsburgh meeting, this may be the first picture of the unified model of AGN. There was equally active work on supermassive black holes. George pointed out Donald's seminal paper in 1969 saying that if quasars are the result of accreting black holes and quasars are a brief episode in most galaxies' evolution, then lots of galaxies, if not all galaxies, should have remnant supermassive black holes. Later on in the 70s, it was realized that the basic process of galaxy formation was dominated by hierarchical merging of smaller subunits. And so if you merge galaxies which each have black holes, you should get larger galaxies which at least start out with more than one black hole. And Roger, Martin, and I explored the possible consequences of this and pointed out that you were likely to get supermassive black hole binaries, which might eventually merge due to the action of gravitational radiation, although maybe they have trouble doing this because of the last parsec problem. But we did point out a number of ways of getting around this, and I'm going to argue that, in fact, it is gotten around. What I'm going to talk about is the relationship of jets or blazars and supermassive black hole binaries, and that topic has been around for a while. There is a particularly well-known object called OJ287, which is a blazar that has a roughly 12-year quasi-period, and in fact, light curve going back to 1880. And here you can see the light curve, and it looks kind of messy, but you can more or less predict when it's going to outburst. However, it's pretty controversial what's going on in this object. It is a quasi-periodic object. The leading idea for how these outbursts occur is that you have a binary black hole, and the smaller black hole punches through an accretion disk surrounding the larger black hole, and so it's a very messy gas dynamical process. There are some fairly detailed models for trying to predict the light curve, but in fact there's a big argument going on over how good these are, and there was a prediction of a major flare in 2022 that didn't actually happen. So most people suspect that this is a supermassive black hole binary, but there's still quite a bit of uncertainty. Now I'm going to argue that in fact there is a new line of evidence that is bringing a lot more clarity to at least some relationships between blazar activity and supermassive black hole binaries, and that is the result of a monitoring program using the 40-meter dish in Owens Valley, which has been monitoring more than 1,800 blazars on a several times a week basis since 2008. And in fact, the results become even more dramatic when combined with a very limited survey in the 1970s and 80s using the haystack dish in Massachusetts. And the discovery is some new examples of varying blazars which actually have sinusoidal light curves. So this is, if you sort of squint, you can sort of see a signal in here. This is data from 1983, from 75 to 83. This is data since 2008. You could fit a sine curve here. You could fit a sine curve here with a different amplitude, but if you use the same period here and extrapolate to the modern data, there is less than 10% phase drift from 1983 to the present time. So there's basically 6 cycles. The period, when you correct for in the co-moving frame, is 2.1 years. And here is the most recent light curve. So you can see that it really is a sine wave. And to just emphasize that, if I subtract this sine wave fit from the data, here are the residuals. Okay, so it's not quasi-periodic. It's periodic, and it's not only periodic, but it's a sine wave. How do you get that? Turns out it's very easy to explain this if it's a supermassive black hole binary. You have two black holes probably in circular orbits, and one of those black holes is carrying a jet which has a fixed orientation in inertial space, but that jet is not only carrying its own velocity, but it's also carrying the orbital velocity. And so you just vector add the orbital velocity to the velocity of the jet and calculate the Doppler shift, and the first order correction is a sine wave. And here's the expression for delta flux over flux. You get a pretty good sine wave signal, even if the orbital velocity in the binary is small, because it's amplified by gamma squared, where gamma is the Lorentz factor of the jet. Okay, so if you try to figure out, if you estimate what the parameters of this binary are, we don't know the mass of the black hole, of either black hole, but for typical blazar masses of 10 to the 8, it's about 1/100th of a parsec. So it's beyond the last parsec problem by a lot. The merger time is very sensitive to the mass, but it could be anywhere from 100,000 to a few million years. The strain, unfortunately, is fairly low. I'll get back to that later. And the orbital velocity you need to get this signal, which is about a 20% amplitude on the sine wave, is only a few percent of the speed of light, so about 0.02 or 0.03. This is a nanohertz. This is a nanohertz gravitational wave source. However, it's too weak to detect currently. Now, I'll just briefly mention some additional support for this binary hypothesis. The most important thing, I think, is the phase coherence over 48 years. However, it does not always produce the sine wave. So it was monitored in the interval, actually, from the University of Michigan radio telescope, and it's just kind of messy. So for some reason, which we don't understand, it turned off in the 80s and turned back on around 2008 or 2009. If you analyze the residuals in various ways, the harmonics are extremely weak. The first and all higher harmonics are about a few percent or less. So it really is a sine wave signal. You can calculate the entire Fourier series for this, Doppler shift model, and it's not too difficult to get that, but it does put some constraints on the parameter of the binaries. Okay, so is this a one-off thing? No, but it's the best case. We have a second example from the same sample, the blazar Parkes J0805-11. That has a period in its rest frame of 1.42 years, and it's not quite as good as sine wave, but they do have 4 cycles. It's pretty noisy. One of the things you have to be very careful of, blazars are very strong red noise sources, so you have to be pretty tricky about trying to make sure that if you only have 2 or 3 or 4 cycles, that the red noise can't emulate the sine wave. But I haven't done any of this. The people who are analyzing the data assure me that there's many, many tests, and we posted this by the 2131 results last week on arXiv. A possible third example is not even a blazar. It's a compact symmetric object, which is like a little tiny FR2 radio galaxy. This hotspot is the thing that's oscillating. There's the sine wave from the last two cycles. Here are a couple of random points from historical observations, and they fit on exactly the same sine wave. Okay. Well, we have enough additional data to complicate the theoretical modeling, which is what I've been mostly concerned with by quite a bit. Here's multi-wavelength data. 2131's been monitored by ALMA since 2014. It shows a similar sine wave at all the wavelengths that have been observed. The OVRO data are at a few gigahertz. This goes up to 345 gigahertz. One thing you may notice here is that, and it's also seen up to optical with the Zwicky transient facility. One thing you may notice here is that there is a systematic phase shift at different wavelengths. And you can fit that to a simple expression, which I'm not going to have time to go into in detail. Now, what's happening is stuff is coming out of the jet, and the jet's moving around. And so at a given phase of the binary orbit, the stuff that comes out just goes outwards and outwards, and then you eventually see it. It emits at some radius, some distance from the source. Then the stuff that's at a different phase does the same thing. And if you see two different wavelengths radiating at this, if you see two different wavelengths at the same time, and they have a difference of a third of a cycle, which is the total phase shift that we see between low and high frequency radio, you would think that that corresponds to 2 years divided by 3. But it doesn't, because as soon as a signal is emitted by a piece of the jet that's at a certain distance from the central source, it starts traveling at the speed of light. The jet itself is moving close to the speed of light, but slightly less. And that difference, however, is crucial because of Martin's 1966 argument. It means that if you see as much as a third of a phase shift, the actual distance between those two emitting regions has to be a third of 2 light years times 2 gamma squared. And in order to get this modulation, you need gammas of between 3 and 10. So we're talking about radio emission coming from tens of parsecs, which is pretty far out for where we think blazar emission comes from. In fact, the spectrum of this source, by the way, this is Planck data. So Planck did do something useful. So this is a Planck spectrum of 2131. And it sort of looks like a typical optically thick radio source. And what this says is that the ALMA signal is coming from, if it's coming from an optically thick region, the jet has to remain optically thick out several hundred light years, which is extremely difficult. It also, the fact that everything fits so well on the sine wave means that the jet material has to be ballistic out to those distances. That's also very difficult because relativistic jets are presumed to be traveling through the inner part of a galaxy, in this case out to hundreds of light years. There's a lot of stuff out there. The jet velocity and direction is likely to be deflected. And so this is posing some very interesting questions about how well we really understand jets. And I'll just say that we are still exploring these, but we think that these phase lag observations are crucial and suggest that maybe under some conditions, jets like this are not continuous flows, but they're actually a sequence of bullets. And there is some precedent for that in a rather different kind of jet. This is SS433, where in fact you can actually see evidence of fairly dense bullets coming out. So the picture we have right now is that this thing is producing a stream of bullets that is able to travel in a straight line for huge distances. I won't talk about possible alternative models to the simple orbital one, but just end by pointing out that this is obviously the kind of source that nanograv is designed, and the other pulsar timing arrays are designed to discover. The locations of both of these blazar sources are exactly in the most sensitive part on the sky for the nanograv array of pulsars. So the red stars are here the pulsars, and the one of these crosses is the highest sensitivity area. The other one is 2131. However, what we are hoping for at this point is no more than an upper limit, because this is still about 3 or 4 orders of magnitude too faint to detect with nanogravity. Nevertheless, in a sample of 2,000, of fewer than 2,000 blazars, we've now detected two sinusoidal light curves with similar periods. If we think about the conditions necessary to actually detect the sinusoids from the Doppler effect, we're probably missing 80% of the sources. So we're talking about probably 10 binaries in the 5 or 10 binaries in the sample. They may have short lifetimes, and all of this suggests that there may be a huge population of very close supermassive black hole binaries among AGN, and particularly blazars. Thank you.